Hello everyone, I'm Xiao Lu from Lubin. Welcome to another session of Lubin Optics Lab. Today, we're diving into two core needs in photonics: fiber collimation and fiber coupling. In fields like signal transmission and system interconnection, we often have to handle two types of light: fiber light and free space light. Turning fiber light into a parallel beam of free space light is what we call collimation. Focusing free space light back into a fiber is coupling. But these two beamforms typically can't be converted directly, because fiber light naturally has a small beam waist and a large divergence angle, while free space optics usually expect a well-collimated beam. That's why we need an optical component to act as a translator. The most commonly used component for this task is the fiber collimator. The key element inside this device is a lens. Geometrical optics tells us that the light emerging from the fiber end face can be treated as a point source. Place that point source exactly at the lens's focal point. The light leaving the other side becomes a collimated beam. That's fiber collimation. Reverse the process. Send a parallel beam through the lens, so it focuses onto the fiber end face. That's fiber coupling. In many experiments, you'll find that fiber coupling is trickier than collimation. Why? Because coupling imposes stricter requirements. The fiber has strict matching requirements for the coupled spot, which come down to three conditions. First, the focus spot must land exactly on the fiber end face. Second, its size must match the mode field diameter. Third, the wavefront curvature at the end face must be flat. All three conditions are non-negotiable. If any one is off, coupling efficiency drops. All three depend on the same parameter: the distance between the fiber end face and the lens. That distance determines, for collimation, how parallel the output beam is, and for coupling, how efficient the launch is. The most common type on the market is the fixed fiber collimator. In these, the fiber to lens distance is fixed during manufacturing, so they work well only when the fiber perfectly matches the collimator's focal length. But in real-life scenarios, the fiber often doesn't perfectly align with that fixed focal length. That's where the adjustable focus fiber collimator comes in. It lets you tweak the distance according to your actual light source wavelength, fiber type, etc., thus improving collimation quality and coupling efficiency and tuning the system to its best performance. Different collimators use different methods to adjust the focus distance. Some rotate a sleeve. Some use eccentric adjustments. Today we'll use a typical adjustable focus collimator to demonstrate the focusing rules and methods for both collimation and coupling. First, follow our selection guide to pick the right collimator for your setup, which you can find from this Lubin mini lecture. Before you start, mount the collimator on a clamp. Ensure that the relative position between collimator and clamp stays fixed. For best results, we recommend using a 3-axis or higher translation stage, like the ones shown here. For coupling free space light into a fiber, you'll need a semiconductor laser, a fiber, an adjustable focus fiber collimator, a 5-axis translation stage, a fiber holder, and a near-infrared detection card. We're using 1060 for nanometers infrared light. Besides, you'll also need a power meter to monitor the coupled power in real time. When you mount the collimator, adjust the coupler and the free space beam, so that the beam hits the center of the collimator lens as perpendicularly as possible. Attention! A noticeable tilt introduces coma and astigmatism, which hurt coupling efficiency. You can use the NER card to check if the spot from the fiber end is circular. If it's distorted, tweak the incident angle. When the spot is circular, insert the fiber into the collimator's fiber port. But don't tighten it yet. Instead, move the fiber connector back and forth by hand while watching the power meter. Stop when you see a clear power peak. This coarse adjustment finds a position where the spot size and wavefront at the fiber end roughly match the fiber's fundamental mode. In theory, we're roughly meeting the spot location condition. Adjust the translation stage, position, yaw, pitch, until the power reading is maximized. Then, push the fiber fully in and tighten the threads. Power will likely drop after tightening. That's normal because the mechanical stress slightly shifts the focus away from the fiber end face. At this point, the focal point is not located at the fiber end face. Now slowly rotate the focus adjustment knob to compensate for that stress-induced offset and restore good mode matching. While you're adjusting, watch the power meter and look for the maximum reading. Keep in mind that when you're close to the best coupling point, the power is very sensitive to focus changes. So turn the knob slowly for even better results. Fine-tune the stage position. Once you find the best coupling point, lock all the components in place. Fine adjustment helps you dial in the alignment and also match the spot size to your needs. While for collimating fiber light into free space, you'll need a beam profiler, also called a beam quality analyzer, and a focusing lens. The laser is fiber delivered. Set up the optics as shown. Keep everything at the same height and along the same horizontal line. Place the beam profiler at the collimator's reference distance. You can refer to the product's detail page for maximum beam waist distance. There are two main ways to adjust collimation. First, we can judge whether ideal collimation is achieved by checking the output spot size. The product is designed based on theoretical calculations, so that at the reference distance, the ideal collimated spot diameter is a known value. When the measured spot size at this position matches the theoretical value, the actual beam waist coincides with the design position, achieving basic collimation. The product page lists the ideal spot size under specified conditions. In practice, your beam conditions may not match the specified conditions. In that case, use ZMax to calculate the theoretical spot size for your setup. Here's how. Open the ZMax file provided in the Lubin Mall. Enter your fiber's numerical aperture and wavelength, and set the reference distance for spot inspection. Set the fiber to lens distance as a variable. Use ZMax functions GBPD and GBPS to calculate the spot size. Rotate the collimator's front knob while watching the beam profiler. Once the spot size matches the calculated value, stop adjusting the fixed focus thread. At this point, you've achieved beam collimation. Alternatively, a focusing lens can also be used to adjust the divergence angle for collimation. As shown in the diagram, set up a focusing lens and the beam profiler. Note that the profiler should be near the back focal plane of the focusing lens. Rotate the collimator's front knob to adjust the internal lens spacing. Monitor the spot size on the beam profiler. When the spot reaches its minimum, meaning the divergence angle is also at its minimum, collimation is now considered achieved. This method is based on the focusing property of a lens. The more collimated the input beam, the smaller the focus spot size. Therefore, when the spot on the beam profiler is at its minimum, the input beam is most nearly collimated. Please note, during collimation operations, since the spot size is small, avoid using excessive fiber beam power to prevent damage to the beam profiler. This is all for today's Lubin Optics Lab. If you have any further thoughts or questions, please leave a comment below for discussion. See you in the next class.